Okay, we're going to pick up where we left off in the last section. Only now what we're going to do is we're going to try to attempt to use the right triangle trigonometry that gave us the trig functions of acute angles and expand that so that we can take the trig function of any angles. Now we've already done a little bit of that involving the unit circle, and as you can see in the diagram I have a unit circle drawn here. And then I have another circle, which I just said was radius r. It could be a larger circle, it could be a smaller circle, it doesn't really matter. Just for convenience sake, I made it a larger circle. And then I have marked an angle, theta, in standard position, and I have it as the terminal side is in the second quadrant. Remember, I mentioned this once before. If an angle is in standard position and the terminal ray or the terminal side is in the first quadrant, we call it a first quadrant angle. In the second quadrant, like this diagram here, is second quadrant angle, third quadrant angle, fourth quadrant angle, and if it lands right, the terminal side is right on one of the axes, it's called a quadrantal angle. But what I'm trying to draw here with the red and the green are two right triangles that are similar. We know they're similar because they're both right triangles and they have the acute angle here that's the same for both triangle. So angle, angle. And the nice thing about similar triangles is, one of the nice things is that we can compare the sides, we can compare the ratios because corresponding sides of similar triangles are proportional. CSSTP. Corresponding sides of similar triangles are proportional. So if I have the smaller triangle here with radius 1, since it's the unit circle, and I have these two sides measured as A and B, now we're going to represent A and B as far as the amounts being, typically we think of these as positive numbers when we're involving ratios, but we can set up the 6 correspondences here using the various sides. And the nice thing about that is, we remember with the unit circle, the cosine of theta would have been where we had intersected the terminal side with the unit circle, that ordered pair would be a over 1. But a over 1 is equal to x over y. And notice here, because of the similar triangles, that for any size triangle here, it doesn't have to be for the unit circle, any size radius here, I can have that same correspondence by comparing, in this case, x over 1 would be, x over r would be the length of the adjacent side here of this right triangle compared to the length of the hypotenuse. Now, again, if we're in the second quadrant, x is going to be negative. This would be a negative over a positive because the length of the hypotenuse is just that. It is a distance, and we're going to consider that as a positive number because we're going to consider that the fact that with a right triangle with sides x and y, that x squared plus y squared is going to equal r squared. R is going to be considered a positive measure. It's not going to be considered a directed measure where it could be positive, could be negative, at least not yet. Soon enough. And you can see I have the other correspondences here with sine, tangent, cotangent, secant, and cosecant. So for any size right triangle here, or for any size circle I should say, I could set up my right triangle and I can do my SOHCAHTOA and I can keep track of my signs as in S-I-G-N-S signs so that I know if it's positive or negative based in the quadrant. Remember, all students take calculus to help us keep track. So we go over here to our nice definition here for trigonometric functions of any angle. Let theta be an angle in standard position where point P is the ordered pair xy on the terminal side, the terminal ray, and we're going to let r represent the square root of x squared plus y squared, which of course we're not going to have that equal to 0 because then we're talking about a point, not a circle. Now we're going to represent that distance from the center of the circle, 0, 0, to that point, xy. Then you can see the following ratios to find the 6 trig functions. The sine of theta is equal to y over r, the cosine of theta is x over r, the tangent of theta is y over x, and there are 3 reciprocals. I think I got them all written down correctly this time. The last time I did something like this, got one of them upside down, or the reciprocal. Now, this is great as far as finding the measures of the values and such, but we can also use something to help us out. Because here's the old man story. I am so old, how old am I? I am so old that we had to use trig tables to find values. We didn't have a calculator. In fact, the calculators that were coming out were very expensive. They were probably $75 to $100, and this is back 1974, 75, and that was a lot of money. I was making a cool $2 an hour busting tables at a truck stop. And the calculator that I got, it didn't have a whole lot of stuff to it. It could add, subtract, multiply, divide. It had memory. It didn't have an exponent button, and it didn't have trig function buttons. I should have spent the extra $25 and got the fancier one that had all that. We had to use tables, and the tables were such that they would only go from 0 to 90. So we only had acute angles. So we used the process of what I'm going to talk about now for angles in standard position. Check this out. I tried to draw a halfway decent circle there. Not so good. And I also tried to draw two intersecting lines through the center of the circle at such a rate that this angle theta and this angle here theta down, they were the same size angle, absolute value wise, same size, which means that these angles would be theta as well. So if you look at theta in the first quadrant, that's the pink mark there. We're looking at quadrant 1, we're calling it just theta. But in the second quadrant, that's the purple one here, where this is 180 and then come back theta. That's its measure. And then in this case here, in the third quadrant, that's the one in brown, I've got 180 plus theta. And then the last one, that's supposed to be an orange color there. In the fourth quadrant, remember this is theta, so that would be all the way around 360 and then come back theta, 360 minus theta. We would have to use these relationships here in the quadrants because look at the ordered pairs. They're either the same exact x value or y value, or they're opposites depending on the quadrant. So in quadrant 1, the sine of theta was y over x, the cosine of theta was y over r, the cosine of theta was x over r, and the tangent of theta was y over x, and of course you have the reciprocals. But in the second quadrant, for 180, the sine, remember the sine is like the y value, so it's still in the second quadrant, it's still positive, was y over r, but in the second quadrant the x is negative, and the tangent of course would be negative. This comes into that play with all students take calculus as well. I wrote these all out. You don't have to write them all down, but I would like for you to look through this stuff because it shows you the relationships with the angles based on theta here being the acute angle. Notice how theta is in all three of these other angles. This one's being obtuse, this one's more than 180 but less than 270, and this is between 270 and 360. And I have broken this down for each one of the four quadrants here. And you can see positive and negative based on which quadrant. But theta is the key here, and we're going to spend a lot of time talking about theta. Theta is known as the reference angle. Now, I didn't have a lot of space to squeeze all this stuff in, so I'm going to give a definition of a reference angle, and I'm going to do some examples in the next video, but this is the relationship as far as the diagram is concerned. So you should look that up. I'm sure you can find this online or in the textbook as well, definitely in my notes. So make sure that you understand these four angles are all related to one another as far as their sines, their cosines, their tangents. They're either going to be the same or they're going to be opposites of one another. And that comes in really convenient. So like if I said, what is the sine of 210 degrees? Well, first off, you should have that one memorized from the unit circle. But the sine of 210 degrees, that would be in the third quadrant. That means my reference angle is 30. And if I know the sine of 30 degrees, which I do, it's 1/2, then in the third quadrant, I know sine is positive in the third, or negative in the third quadrant, so I know that the sine of 210 degrees is negative 1/2. I'm going to be using these relationships to help me determine the values of the various trig functions. But first, we've got to define what a reference angle is, and we're certainly going to look at some examples of this.